Hello guys, good morning, and today, welcome to the stream. Today we're going to be doing, in Khan Academy, Algebra 2 functions. We're going to be doing modeling situations by combining and composing functions. So first we'll start with this video, and then we'll move on from there.
Iffy is building a tree tower, which is a tower built on top of a tree. The tree is currently 5 meters tall, and Iffy has found it. I don't know if it's Iffy or Ify, and Iffy has found it is growing by 0.1 meters a month, or a tenth of a meter a month. The tower is currently 2 meters tall. So this tower that sits on top of the tree is 2 meters tall currently, and Iffy or Ify adds to it at about 0.2 meters a month. So I guess he or she, I don't know if he, well, let's just say he, is continuously building this tower on this continuously growing tree, which is fascinating. All right. The function a of m returns the tree's height in meters m months from now. Fascinating. The function b of m returns the tower's height in meters m months from now. So this is the tree's height. A of m is the tree's height. B of m is the tower's height. Find the formula of the two functions. So a of m, so they tell us the tree is currently 5 meters tall. So it's going to be 5 meters tall right at the start. And then every month it is growing by 0.1 meters. So it's going to be 5 plus 0.1 times m. And this m here, this is not meters, this is actually the month. Remember, m returns, m is the number of months. This m here, so after 0 months, which is right now, where this is just going to be 5. After 1 month, it's going to be 5.1. After 2 months, it's going to be 5.2, which is exactly what we want. All right, now let's think about the tower. So the formula for b of m. So the tower is currently 2 meters tall. So it's currently 2 meters tall, and it grows at 2/10 of a meter per month. So 2/10 times the number of months. And once again, this m right over here is not meters. I'm not writing the units here. We're just assuming that whatever this returns is in meters. This m right over here is the number of months that pass by, the number of months from now. All right. The function c of m returns the vertical distance between the ground and the top end of the tower. Makes sense. That would be from the bottom of the tree to the top of the tower. Write the formula c of m in terms of a of m and b of m. Well, the total height is going to be the height of the tree, which is a of m, plus the height of the tower, plus b of m, plus b of m. That's what c of m is going to be. And then they say write the formula of c of m in terms of m. Well, we just need to add these two functions. If we add 5 plus 0.1m to 2 plus 0.2m, that's going to be, let's see, we could add 5 plus 2, and we're going to get 7 plus, and if I have 0.1m and I add another 0.2m, that's going to be 0.3m, 0.3m. And we are done. We got it right.
Alright, now we're going to watch the next video.
Carter has noticed a few quantitative relationships related to the success of his football team and has modeled them with the following functions. All right, this is interesting. So he has this function which he denotes with capital N, and it's the winning and the input of it is the winning percentage W, and then the output is the average number of fans per game. So he's making some type of model that says, look, the number of fans per game are going to be in some way dependent on what your winning percentage is. And I'm assuming his model, the higher the winning percentage, the more fans are going to show up at a game. Now this is the W. The input is the average daily practice time, X, and the output is the winning percentage. All right, that makes sense. Probably, once again, probably some type of a positive effect of practicing more is going to create a higher winning percentage. And this other function, number of rainy days are, and then average practice time. Yep, well, the more rainy days you have, well, that's going to lower your average practice time. So I definitely see how practice time P would be a function of number of rainy days. The expression n of w of x represents which of the following? Well, before we even look at the choices, let's think of what's happening. This is another way of denoting we're going to take x. We're going to take x right over here. And we are going to input it into w. And we're going to get out w of x. And then we're going to input that into the function n. And we are going to get out n of w of x. So what does the function w do? What does the function w do right over here? Well, that's winning percentage as a function of practice time. So you input practice time, and it gives you what somehow predicts a winning percentage. Winning percentage. And then you take that winning percentage and you input it into function n. Function n is going to output the number of fans per game based on winning percentage. So this is number of fans. So when you take the composite function, you're actually creating a function that starts with practice time as the input and shows the number of fans that are going to be dependent on your practice time. So this is interesting. So we should look for a choice that says, how does the number of fans that show up at a game, how is that dependent on practice time, x? All right. The team's winning percentage is a function of the average daily practice time. Now that would be just w of x. If they said just w of x, that would be winning percentage as a function of average daily practice time. So I can cross that one out. The average number of fans per game. All right, this is interesting because that's what the final output is going to be in terms of the average number of fans per game. That is the output of the function n right over here. The average number of fans per game as a function of the number of rainy days in a season. Nope, we're not doing that. We're doing it as a function of practice time. You could construct that. In fact, if you wanted to do this, that would be n as a function of w as a function of p of r. So that would have been this choice, where you input the number of rainy days. From that, you're able to figure out practice time. And then you input practice time to figure out win percentage. And then you input win percentage to figure out the number of fans in the crowd. But that's not what we're doing here. We're just starting with daily practice time and getting to fans per game. So let me rule this one out. And if you found this one a little bit, what I just did a little bit confusing, I encourage you to try to set up a diagram like I just did in the beginning of saying, oh, well, look, we could start with R to use that as an input to get average daily practice time, and then use that as an input into W to get winning percentage, then use that as an input into N to get average number of fans per game. But that's not what they're describing for N of W of X. The average number of fans per game as a function of the team's average daily practice time. Yeah, that's what's going on. You have your average practice time x being inputted into the function w. So your average practice time is going inputted into w, and it outputs winning percentage, which you then input into n, and to get the average number of fans per game. The average number of fans per game as a function of the team's average daily practice time. So yep, I definitely like that choice. Let's do another one of these. This is interesting. Denise studied the park near her home, where she identified several quantitative relationships and modeled them with the following functions. So B, it inputs the height of a tree in terms of x, and it outputs the number of birds nesting in that tree. H, input the average temperature at a specific location, and it outputs the height of the tree at that location. And T, the altitude of a specific location, and then if that's the input, and then the output is the average temperature of that location. All right, this is interesting. According to Denise's findings, which of the following expressions represents the height of a tree as a function of its altitude? So we want to figure out, we want to output the height of a tree, and we want to input the altitude of a specific location. So let's think about it. If we take our altitude at a specific location, r, and we input it into the function t, out of that, we're going to get t of r. Let me write that a little bit neater. We're going to get t of r, which would represent average temperature at that location. Average temp. And then if we take the average temperature at that location and input it into function h, and then we input into function h, we are going to get the height of a tree at that location. So we're going to get h of t of r. And so this is going to be height of tree at that location. Height of tree. And so there you have it. H of t of r. You start with r, altitude, a specific location, input into function t. T is going to spit out the average temperature at that location. You input that into h, it's going to get the height of the tree at that location. So h of t of r. H of t of r is this choice right over there.
Alright, so now we're going to move on to the next video, which is modeling with composite
Fuel
functions,
is being
example
pumped
2.
into a storage tank. The volume V of the fuel in the tank depends on the depth d according to the formula V of d is equal to 4 times 3d squared plus 5 to the third power, where d is measured in meters. Suppose that the depth d of the fuel depends on time, measured in hours according to the formula. D of t is equal to 1 over the square root of 3 times the square root of t minus 5. And that makes sense, that if I'm pumping something into a storage tank, the depth of what I'm filling, of the fuel, I guess is what I'm filling, is going to depend on time. And then the volume could be dependent on the depth. Use function composition to write the volume of the fuel in the tank as a function of time. Simplify your answer as much as possible. So let me get my scratch pad out. So I've already written what they told us here. This is volume as a function of depth. And now this is depth as a function of time. So if we want volume as a function of time, what we really want to do is figure out what is, so we could take V of d, we could say V of d of t, V of d of t, d of t. Now this will give me volume as a function of time. So everywhere where I see a d, I should replace it with this description. I should replace it with this description of how does d vary with respect to time. So let's do that. So V of d of t is going to be equal to 4 times 3 times d squared. But instead of writing d squared, I'm going to write all of this business squared. So 1 over square root of 3 times the square root of t minus 5. All of that squared. Plus 5 to the third power. I really hope this simplifies in a reasonable way. So let's see. Let me actually copy and paste this so I can have a little bit more real estate. So let me just paste it down here so I can work it out. All right. So then we get this is going to be equal to, let's see, if we square this right over here, and I could do it all in, so this is going to be 4 times 3 times this whole thing squared. So this whole thing squared, 1 over square root of 3 squared is going to be 1/3. 1/3. And then square root of t minus 5 squared is going to be t minus 5. And then, of course, we have plus 5 to the third power. Let's see, 3 times 1/3. Well, that's just going to be equal to 1. And so we are left with, this is equal to 4 times t minus 5 plus 5. This does simplify nicely. Plus 5. So we're going to be left with 4 times t to the third power. 4 times t to the third power. So let's input that into our, so v of t, and let me just make it clear. This is now v, this is giving our volume as a function of time. We can now say that this is v of t. V of t is 4t squared. Once again, this is the volume as a function of time. You give me a time, I'll tell you what the volume is. So 4t to the third. 4t to the third power. V of t. Did I say 4t squared? I don't know. Sometimes I do strange things. I said 4t to the third power. 4t to the third power. I did format it correctly. And then there's a second part of this question. How many cubic meters of fuel are in the tank after 2 hours? Round your answer to the nearest tenth. Well, 2 hours, that means t is equal to 2. They say t is measured in hours. So when t is equal to 2, the volume is going to be, so 2 to the third power is 8. 8 times 4 is 32. 32. And let's check our answer, and we got it right.
Alright, now we're going to go back to the lesson page and start some practice. Devra is filling a pool with a hose. The volume H in liters of water coming out of the hose in m minutes is given by the function h of m equals 17.4 m. However, it is a sunny day and the water is also evaporating from the pool. Therefore, the volume V in liters of water in the pool in the V in liters of water in the pool in minutes after Devra starts filling it is given by V of m equals 17m. Let E be the volume of water in liters that has evaporated from the pool in m minutes after Devra started filling it. So the volume H liters, water is coming out of the hose in m minutes. So this is how much water is coming out of the hose per minute. And then this is how much water is in the pool in minutes after. So E of m would be how much water is evaporated in m minutes. So we want to take the, well, this would be how much is going into the pool per minute, and this would be how much is coming out. So we'd take 17.4 minus 17, and that'd just be 0.4 per minute, like 0.4 liters per minute. So so it'd be H of m minus V of m, right? So that'd be 0.4 m. So we'll check our answer, and we got it right. So move on to the next question. The distance and time that Amelia runs each day depends on the number of hours, h, that she works, and the distance d in miles, and the time t in minutes that she runs are given by the function. Distance as a function of hours is negative 0.5 h plus 9.5. And t in time in minutes of hours worked is negative 5.5 hours plus 92.5 respectively. So each of the, yeah. Let R be the average speed that Amelia runs on a day in which she works h hours. So write a formula, R of h in terms of d of h and t of h. So rate equals distance divided by time. So we have to do d divided by h. So d of h over t of h. And then now we have to simplify it. So it'd be negative 0.5 h plus 9.5. And then on the bottom, negative 5.5 h plus 92.5. And I think that's the answer. Nope. So we're going to check, see what we did wrong. Yeah, so we have distance over time. We got that right. And then we plugged in the things. So I had a capital H here, and that was all we got wrong. So we did pretty much get it right. You gotta watch out for those little things; they'll get you. Um, so a partially filled pool has 10,000 liters of water in it when Finn begins to fill it with the hose on a hot sunny day. The volume V in liters of water coming out of the hose in m minutes is given by the function V of m equals 20m. And the volume E in liters of evaporating water in minutes is given by the function E of m equals 0.1 m. Let P be the total volume in liters of the pool in m minutes since Finn started filling it. Write a formula for P of m in terms of Vm and Em. So we want to find the volume of the pool in minutes since he started filling it. So using V of m and E of m. V of m is how much water is coming out of the hose, and E of m is how much is evaporating. But the pool started with 10,000 liters, so we're going to start with 10,000 liters. We have 10,000 liters, and then we're going to add the amount that's coming out of the hose, V of m, and then we're going to subtract the amount that's evaporating, E of m. So now we want to write one in terms of m. So it would be it would be 10,000 plus 20m minus 0.1m, and then that can be simplified down into 19.9m. So we'll go with 19.9m, and then we'll check, and we got it right. We'll move on to the next question. Rokio predicts that the amount of corn C in bushels produced on her farm T years from now can be modeled by the function C of T equals 80T plus 1,000, while price P in dollars per bushel of corn T years from now can be modeled by the function P of T equals 0.03 plus 5. So amount of corn in bushels is C of T, and the price in dollars per bushels of corn T years from now can be modeled P of T. So let I be total income from producing corn T years from now. So this would be if she produces Rokio, he or she, not really sure how to pronounce that name either. C produced on her farm T years from now. So it'd be, this is how much corn is produced every year, like in the future, so it'd be C of T for the amount of corn times P of T for the price of corn. So you multiply the amount of corn by the price of corn, and that'll tell you how much he's going to make. So write a formula for I of T in terms of T. So now we just have to write each of these out. So it'd be 80. Oh, we need parentheses. 80T plus 1,000 times 0.03T plus 5. So I'm going to actually pull out the writing pad to work on. Alright, and then, so we're going to do 80T plus 1,000 times 0.03 t plus 5. So we're going to do 80t times 0.03, and that's going to be 24. Wait, let me think about this for a sec. I think it's going to be 80 times 0.03. It's 2.4. So I was off by a decimal place. 2.4 t, and then we're going to take 80t times 5, so plus 400, right? That's 40. Um, Now we multiply by 1,000. Just going to go 1, 2, 3. So it'd be plus 30 t. Oh, this one's going to be t squared. Yeah, because it's 0.3 t, so it's going to be t squared, because t times t. And then we're going to take 1,000 times 5. It'd be 5,000. So this is 32.4 t. No, 2.4 t squared plus 30 t. Okay, so get rid of all of this. Everything inside the parentheses. So it's going to be 2.4 t squared plus 30t plus 5,400. Then we're going to check our and we got it wrong. So we're going to see what we did differently. We have c times p of t, and then we had this. We did have that. When we multiplied the 80t times the 5, we left off the t. Never forget about your variables. That seems to be what's gotten me like every time. It's 430, and it's just 5,000. Just simple mistakes. Alright, next, we're going to move on to the next exercise for practice. Procky, the office manager at a private practice, identified several quantitative relationships surrounding a patient's visit and wait time and modeled them with the following functions. P, the function P, input the time of day and it outputs people in the waiting room. Function L takes the people in the waiting room and outputs the average length of the visit. Function W, people in the waiting room, and it outputs the patient's waiting time. So which of the following represents a patient's waiting time as a function of the time of day? So we want the very inner one to be the time of day, because that's what we want the input to be, as a function of the time of day. So that's the input. And the output, we want to be the patient's waiting time. So we'll find which one outputs the patient's waiting time, and that's W. Well, W of the people in the waiting room. So we take the people in the waiting room, which is output by the function P. So we have W of P of the time of day, which is T. W of P of T. So that's this one right here. We'll check and we got it right. And Burian is a very prolific writer, able to write thousands of pages per day. His assistant identified a few relevant functional relationships and modeled them. P, amount of sugar in Burian's morning coffee, outputs the number of pages Burian writes. I, inputs the number of pages Burian writes and outputs the number of ink cartridges used. And S, inputs the amount of ink cartridges used and outputs the number of times the assistant has to walk to the office supply shop. So the expression S of I of K represents which of the following? Well, if we start with S, actually let's start with K in the middle, which is the number of ink cartridges used. I of k is the number of pages Burian writes, outputs the number of ink cartridges used. And S is the number of ink cartridges used and the number of times the assistant has to walk to the supply shop. So this is all gonna output the number of times the assistant has to walk to the supply shop as uh, a function of the number of ink cartridges used, because that's the output, and it goes right into the input of S. So it's going to be the number of times the assistant walks to the office supply shop as a function of the number of ink cartridges used. So the number of times the assistant walks to the supply shop as a function of the amount of sugar in Brian's morning coffee. That's not right. The number of times the assistant walks to the office supply shop as a function of the number of pages Brian writes. That's correct. We have the number of pages Brian writes, which outputs the number of ink cartridges. So that's the one we want. All right, now we have Anais, a math teacher, noticed that the average grade on an exam, G, given that N students watch the related video, can be given by the function g of n equals 50 plus 1.5 n. She also noticed that the number of students, S, who watch an m-minute video can be modeled by the function S of m equals 30 minus m. Find an explicit expression that gives the average grade on an exam. So this is G, gives the average grade on an exam of if the related video is m minutes. Sorry guys, had a yawn there. So we want the grade as an expression of the length of the video in minutes. So you need to input into this one how many students watch it, which is the output of S. So we want G of S of M. So we're going to open up a new one here and zoom in a little bit. So we want explicit expression, so I think we want is to plug in S of M everywhere we see in G of N. So G of S of M, sorry, equals 50 plus 1.5, and then we want to plug in S of M right here. And we're just going to skip the step where you write S of M and then plug it in. We're just going to write in what it is. It's 30 minus M. So now we want to multiply out. We'll have 50 plus 15. No, not 15. Plus, well, 30 times 1 is 30. Plus 15 would be 45. Minus 1.5 M. So we have 95 minus 1.5 M. And that would be G of N. So this is the average grade. Here, actually, this is the average grade of the class with a related video to the test that is in minutes long. So So it should be 95 plus 1.5, no, minus, I always mess up on the little mistakes, 1.5 m. 95 minus 1.5 m. And we got it right. So we'll move on to the last question. Robert is a stuntman planning his jump off a bicycle ramp and over an array of trucks. He identified a few quantitative relationships and modeled them here. So the function s inputs the height of the ramp, outputs the speed at the edge of the ramp. The function d inputs the speed at the edge of the ramp and outputs the distance of the jump. And the function t inputs the distance of the jump and outputs the number of trucks Robert can jump over. So which of the following represents the distance of Robert's jump as a function of the height of the ramp? Well, we want something that'll output the distance of Robert's jump. So that would be d. So we want something that has d on the very outside. But we'll just work through the rest as a function of the height of the ramp, which would be this right here, because you input the height of the ramp, you output the speed at the edge of the ramp, you input that into d, and you output the distance of the jump. So it'd be d of s of r. So we'll check, and we'll show summary. And that's all for modeling situations by combining and composing functions. Thanks for watching the stream, and goodbye. I will be streaming tomorrow. Tomorrow I'll be streaming the first quiz in here and shifting functions. So thanks for watching.